Thank you very much for inviting me. And so let me start. Okay, here's the title. And okay, so let me start from a kind of disclaimer. So what I won't discuss on my talk. So usually in complex analysis, when one speaks about result concerning sharing values, usually one has in mind results similar to this famous Newman-Lina 5-value theorem, which says that if you have two non-constant meromorphic functions on C sharing 5 distinct values, that means that they have the same inverse image for each of these 5 values, then these functions are equal. So in my talk, I will speak about algebraic things. So for example, about rational functions on the Riemann sphere, or about holomorphic functions, maps on compact Riemann surfaces. And therefore, in this setting, we don't have much interesting. No, just because, for example, if you have two rational functions, then a simple application of the Riemann-Gurewitz formula implies that if they share in this sense 4 distinct values, then these functions are equal. So let me explain why in 2 words. But basically, you should just consider the function f minus g, and you can calculate the degree of this function, no, estimate at least, and estimate the number of points in the preimage of these 4 points. And you will obtain that f minus g has too many zeros, okay? And therefore they coincide. So now the problem of describing rational functions sharing preimages became much more complicated if we consider, instead of preimages of sets, preimages of points, preimages of sets. And even in the polynomial case, it leads to difficult problems. So let just me mention this problem which remained open for nearly 20 years. So assume we are given 2 complex non-constant polynomials of the same degree. And we know that preimage of the set which contains exactly 2 points, -1 and 1. So the preimage of the set is the same under P under Q. So again, we consider this equation as a set-theoretic equation, meaning that we don't take into account multiplicities, or we don't know to which point in preimage correspond points. So we just take 2 points set, consider preimage, we obtain some set, and ask, is it true that such a condition implies such strong consequences? So now let me formulate the main problem I will discuss today. So we start from 2 rational functions, or more generally from 2 holomorphic maps on a compact Riemann surface. And we take some compact set K, sorry, not compact, but just a set. And we assume that we have such an equality. So the question is following. So what can we say about these maps and the set K? I also will consider a similar equation, which is a little bit more complicated, because now we have 2 distinct sets, okay? But still we consider this condition. So I will present several results which are completely different and require different techniques. So the first one, when K is a compact set in C. The second one, when K is contained in a number field, or more general and finitely generated field. And the last case, when K is contained in the field of real numbers. So of course, because it's a web seminar, I will try to connect this problem to number theory. Say the second one already is more or less connected, and I will show that other are connected too. So maybe not in a direct way. So now let me give an interpretation of this problem in terms of the of correspondences. It is important also because it kind of it gives us a motivation for our study. So I recall that a correspondence defined by an algebraic curve is just a multi-valued map that assigns to a point x the set of all points y such that this condition is satisfied. So along with this forward map, one can also consider a backward map defined similarly. And actually, instead of a curve, one can take as the primary object of investigation just a pair of holomorphic map on a compact Riemann surface that parameterize this curve. So why this happens? No, just because from this point of view, if we work with functions parameterizing our curve, we see that forward and backward maps are just given by these multi-valued functions. Okay, so we take Q of P inverse of Z. And now the correspondences can be naturally composed, and their dynamics recently have been extensively investigated. So from different perspectives, so also in numbers or also as a kind of generalization of classical complex dynamics, and very, very many aspects you can find here. And so eventually, in this context, describing the sets satisfying this equality is exactly equivalent to describing the completely invariant sets of the associated correspondences. And of course, this is kind of fundamental question. So what could be these completely invariant sets? In particular, if they are compact or if they are contained in a number field. So, and from this point of view, it is, well, one can say it's kind of a justification for this activity. Also, I started interested in these things even before then I knew what is a correspondence. Okay, but particular case, if we have just rational functions, just corresponds to the situation in which the curve we consider has genus 0. But from this interpretation, it is clear that we don't have any reason to restrict ourselves by rational functions. It's much more natural. Consider arbitrarily holomorphic map, but even if we speak about general correspondences, you can consider just two maps and probably even two different curve and not necessarily define a type C and so on, but I won't consider here such a generalization. Okay, so now it's the first part, so sharing preimages of compact sets. So let me start from recalling some stuff which is very classical, very old, and maybe one can say even old-fashionable. So now it's not that popular, but 100 years ago it was. So, and even before, because it's something which goes back to Chebyshev, Tonelli, Vallée-Poussin. So I recall that if we are given a compact set in C and monic polynomial P of degree n, so we say it is nth polynomial of least deviation from 0 if this equality is satisfied. Its norm is minimal, so for any monic polynomial of degree n, whereas the norm is the standard maximum supremum norm. Okay, so in other words, so its value, its maximal value, is less than any other such a value for polynomial. So The result, so first it is quite easy to show that such polynomial always exists, but a little bit less trivial is to show that it is unique whenever the set K contains at least n points. So it was first proved by Tonelli and some version by Vallée-Poussin, and also by Kolmogorov in a much more general setting, but it is also was in Kolmogorov's work. So now let me start from this theorem, which I proved when I was a PhD student. So that's why I like this topic, probably old laugh. So here is the theorem. So let's start from any monic polynomial of degree n and take any complex number alpha. So then we can consider this preimage, and the theorem says that this polynomial will be automatically nth polynomial of least deviation on this set. So again, we start not from a set, we start from a polynomial and a point. Then we take symmetric point, and then we take preimage. This preimage is a set, and the theorem says that for this set, this polynomial is polynomial of least deviation. So how it is related to the subject I discussed? So because we immediately obtain a solution of this Young problem. So if we have two polynomials of the same degree such that preimages of -1 and 1 are the same, then polynomial should be equal or plus minus equal. So what is the proof of corollary? So proof of theorem, I don't have time, but well, it's kind of tricky calculations, and the corollary, to prove a corollary, we just should say that we can pass from our original polynomials satisfying this condition to monic polynomials by dividing by the leading coefficients. So we obtain from this condition, and therefore by this theorem, P should be equal some constant by Q. But now, what is this constant should have modulus 1. Why? Because if these polynomials both are polynomial of least deviation, so this deviation, this maximum, should be the same. But maximum is given by this number, no absolute value. Therefore, absolute values should be the same. Therefore, we have such an equality. And eventually, we can again return to our condition. And it implies easily that this map should send the set -1, 1 to itself. Therefore, P equals plus minus Q. Okay, so in the same way, one can prove a bit more complicated result, which says that if we have just two polynomials of the same degree, then this equality for any compact set implies more or less the same thing, just with the distinction that now P equals some polynomial of degree 1, which should transform our set Q to itself. So really interesting question now is following. So what happens if degree are different? Because we obviously have already a lot of examples like that. So we can take any power and, or any Chebyshev polynomial. And for such polynomials, we obviously have these equalities satisfied. So, and from these solutions, we can generate some fuzzy solutions, just composing our P and Q with some polynomial V from right side. We will see this condition a lot in the talk. Okay, so now a very interesting result of Ding is a description of all polynomials of arbitrary degree such that this condition is satisfied. So for infinite compact set K, so first it was proved under some additional restrictions regarding logarithmic capacity, and in general case in the second paper. So the methods of Ding were completely different. He used complex dynamics, basically. And so what is the answer? So then A is a P and Q as above. This means coming from powers of Chebyshev may be composed with some polynomial W. Or the third option is that P is related to Q in this way. So you see it is a little bit similar, but now instead of polynomial of degree 1, you have arbitrary polynomial, not necessarily of degree 1, and it satisfies this condition. So K is completely invariant set for this polynomial C. And the last stage is to ask what happened if we allow not only different degrees, but also different sets here. And it turns out that it's also possible to solve completely. So, okay, let's assume that we have some polynomials satisfying this functional equation. Okay, then we have kind of commutative diagram, and it's easy to see that if we now take any compact set K3, and now we can go back in this way, or we can go back in this way. But obviously that if we take K1 just preimage of K3 under F, and K2 preimage of K3 under G, we are done, we obtain this condition. A very general, a very simple way to obtain solutions. And so the point is that all solutions to this equation can be constructed in the above way, provided that the set, what we have here, we have some compact set, so it should contain at least LCM points. Therefore, it is more strong than, for example, a result of Ding, because we don't require that our sets are infinite. But on the other hand, what is interesting that this result can be used for proving the Ding result much more easily than the original proof of Ding. But it's not a direct corollary. You still should do something. So because, well, here you have a very general equation, and here you have very few solutions. And but it is possible. Okay, so now this theorem has a lot of applications, and it has applications to known problem, like for example, description of polynomials sharing Julia set. Also has application to description of commuting and semi-conjugate polynomials. And also maybe most interesting, because this things are new, is application to description of invariant curves for polynomial endomorphisms of product of P1. So why it is so interesting? Because such endomorphisms serve as a framework for testing various conjectures in arithmetic dynamics. For example, I know Janka conjecture, and it was seminal paper of Medvedev and Scammon, where they investigated invariant curves for such endomorphisms, and so on. So it is interesting, but the real problem I would like to mention is that all these methods, also by Ding or in my own works, are restricted to the polynomial case. And the problem of describing rational functions sharing preimage of compact set is completely open. So the one result which is related and very strong and interesting, which is, however, do not solve it in the sense, in the previous sense, is following. showed again. So he worked with correspondences. So his formulation is a little bit different, but in our setting, it exactly says the following. So if you have two holomorphic maps on a compact Riemann surface satisfying this condition, now for infinitely many finite sets. So here is the condition he used. Then there exists a rational function f such that f of p equals f of q. So you can see again that we have some specific functional equation. And of course, if you do have such a functional equation, you can do the same trick as here. So of course, you can construct from these equations solutions of this equation. But what is important here is that in rational functions, you have kind of non-trivial solutions of this equation. And in the polynomial case, they are mostly trivial. So I won't explain in details what does it mean, but just believe me. So it is indeed something interesting for rational functions. And here is the result. Here is the result. So now let me pass to the following part. So now what about if we consider preimages our number fields? So first of all, I would like to make some preparations to introduce some very simple definition. So just to mention, so describing solutions of this equation where K1 and Q are subsets satisfying certain restrictions, that doesn't matter, so we fix some restriction. So it reduces to describe a solution for which these maps have no non-trivial common composition right factor in the following sense. So the equalities I wrote here, where these maps are holomorphic maps, imply that a degree of W is 1. So so first of all, let me stress that, of course, you can state this condition in the standard language of field extension. Okay, like a composite of fields should be the field of all functions. But when working with these preimages, it's a little bit maybe more convenient working with such a representation of the same property. Because of what? So if you know that these preimages coincide, you obtain quite easily that also these preimages coincide. Therefore, you can assume from the very beginning that you don't have such factor, and this is usually will be my assumption. Okay, I just wanted to explain that it's natural, so it's not a restriction. So now let me give an example which will show that the situation is now different. So let's take as K just the set of squares of integers, like 1, 4, 9. Then for these two polynomials, your preimages both are just sets of integers. So you have a non-trivial solution of this equation. And what is interesting that this solution looks completely different in the following two aspects. So as you remember, so for example, for polynomials, we expected that if they have the same degree, so that it should be something like that. P equals some polynomial of degree 1 of Q. But we can see that now it's not the case. No, just because, for example, these two polynomials have different critical points. And by composing them from left by some other polynomial of degree 1, you cannot change these critical points. You can change critical values, but not critical points. So you see that it's something different from this point of view. But also, as you remember, the result of Belaish, so you can see that this condition also is impossible, obviously. Why? Because as you see, Q is just a shift of P. Therefore, if it held, we would obtain some rational function like that, which is just invariant under the translation. Of course, it is not possible because, well, we don't have infinitely many zeros, for example. Okay, so you can see that solutions exist and they are completely different from solutions we obtain assuming that our sets is compact. Okay, so now again one definition, again just on the language of maps instead of standard language of fields. So we start from a map on a compact Riemann surface, and we say that the normalization of this map is just a compact Riemann surface together with some holomorphic Galois covering of minimal degree, such that we have this equality. Okay, so it's a left factor. Of course, so to understand what this normalization, you just should think about field extension. So you start from this field extension where Q is, sorry, okay, yes, you start from Q, you consider this field extension, and then you consider this Galois closure. Okay, so from algebraic perspective, it's exactly this, and from point of view of functions, you obtain this. Okay, so now what is the result, which is relatively simple, which concerns this situation. So we have two holomorphic maps without right factor and two sets such that this condition is satisfied. For some infinite sets contained in a number field or infinitely generated subfield of C. Then genus of both normalization is at most 1. So of course you understand, of course you obtain immediately that the genus of R should be at most 1, but it's not that interesting, because what is really important is that Galois covering from surfaces of genus at most 1 are easy to describe. In fact, if genus is 0, you just obtain the classical Galois covering from the sphere by to the sphere described by Klein. So okay, if you have genus 1, it is a little bit more complicated, but you still have some reasonable description, and in particular you know what branching of these functions could be. So therefore, at least if you take some random functions, for sure you cannot obtain something like that. So the conclusion of the theorem follows from the following statement, which is more general in a sense, but more general probably it's better to say that use weaker assumptions. So if we have some infinite set, subset of finitely generated field, then mirror the inclusion okay, I probably missed here some words, but okay, so the idea is that if you have this, then necessary genus of normalization is at most 1. So in a little bit more classical terms, this means that if you have an algebraic curve, and you know that there exists finitely generated subfield and infinite subset in this subfield, such that for every y from S, all y fiber of X belongs to the field, then the Galois closure of this extension has genus at most 1. So I didn't see this result published, but well, I guess specialists somehow understand it, like it's not that deep. So the idea is just to use the Falting's theorem applied to this algebraic curve. So, well, you obviously have a lot of infinitely many solutions in this number field, but the point is that how it is related to the normalization. It is related, for example, again, you can work algebraically, but if you still choose this approach, so this is nice description of this Galois closure, which seems to go back to Kronecker. So if you have algebraic variety with some, sorry, if you have some holomorphic map, it can be rational functions or any holomorphic map. So you just consider such a variety where everything equals. And then you should remove all components which belong to the big diagonal. And you obtain some collection of components. So they all will be isomorphic. And moreover, they all will be isomorphic to the normalization. So this is a nice description. Okay, so it is especially, I think, useful if you work with rational function, because you just obtain an equation for Galois closure, okay, explicitly, absolutely explicit. And using this fact, you can show that this curve has infinitely many points, and using Falting's theorem, you obtain the conclusion. So now we can ask if the assumption that these numbers are at most 1 is sufficient for the existence of field and set as above. It's not that obvious, because we used some weaker condition, and but what is also simple is to show that if you have two holomorphic Galois covering on a surface of genus 0 or 1, then you can easily construct such sets. So you just should take some group generated by the group of covering transformations. Let's assume that we work on a Riemann sphere. And then you can add some Möbius transformation of finite order, but it's just, okay, I will say later. So, and now you take some arbitrary point and you consider some orbit, okay? So because it is an orbit of group generated by all these groups, so it is a union of orbit for each of this group, and therefore you can find some sets such that this condition is satisfied. And but the point that sometimes you can arrive in certain senses. So if this group can be finite, and in this case one can show that you will obtain solutions of this sort, okay, like here or like here, but in general not, because in general you will face the situation, oh sorry, face the situation like here. So it is not possible in general for this example, because you have here some Galois covering, here some Galois covering, and here two rational functions, maybe not necessarily equal as here. But anyway, the rational function you obtain should be invariant with respect to the whole group. So in case if this whole group is not finite, and for example here you just take something like that, so you cannot obtain this equation, okay? Okay, so now more interesting result, which already requires this condition. So it is not enough only use things like that. So says eventually, so now if you have preimages of the same set, which are the same, so again, you can find a holomorphic Galois covering, define it on a compact Riemann surface of genus at most 1. But now both P and Q should be a left factor of this one Galois covering. So, and now, what about examples? So what I'm able to do is to show that, again, now we have two left factors of the same Galois covering. So what I can prove that at least if you have Galois covering of this type, so one is P, and the other is just P composed with some Möbius transformation. So it is also Galois covering, but very, very close to this one. And for this Galois coverings, you can construct such a set K. Now, an interesting question. Is it, does it give you all possible examples? Again, so the condition is only that they should be some left factors of Galois covering. But if it is true if we are giving such a covering that for all factors like Z, we can construct such sets. So the answer is not known to me. But what is interesting that using completely different techniques, it is possible to show that these conditions are not sufficient in the sense that we have some other restrictions. Namely, it is possible to show that if you have two rational functions such that preimages coincide, then they should have the same degree. So you see, it is not directly related to this result. So in this result, they just, well, left factors. But in the examples, they do have the same degree. Okay, so it is formulated for number fields, but actually it is also true for finitely generated. But what is the idea? Here again, you can use some more general facts. So you consider two non-constant rational functions, some infinite subset of your field, and then you consider this condition that this preimage is a subset of this preimage. So the conclusion is that the degree of B should be more or equal degree of A. So in particular, if you have the equality here, it implies that degree should be equal. Okay, so this gives you a result. And proof here is completely different, and it's somehow similar to the argument involving the weight height for the fact that inverse orbit of a point under a rational function contains only finitely many points in any finite extension. And but here, instead of the orbit of rational functions, one should consider the orbit of this algebraic function and use the existence of a finite set whose orbit under this H, I didn't scare H, is infinite. So just let me mention that, yes, if degree is equal to degree of B, then such a set may not exist at all. For example, if you have this relation from Deleuze result, you cannot find K like that because they all will be finite. Okay, and in principle, so what is used is only basic equality for heights, and therefore you, instead of Weil height, you can take Marivaki height and obtain this the same result for arbitrarily finitely generated field. Okay, so now the last part of my talk. So let me start from recalling what is a Belli function. So a rational function, we will speak only about rational functions now, is called a Belli function if it has only critical values -1, 1, and infinity. So if you take the segment -1, 1, color the point 0 in black and the point 1 in white, and consider this preimage, we obtain what is called descent on fun, or simply descent. So it is by definition a connected planar graph with a bipartite structure. Black vertices are preimages of 0 and y vertices are preimages of 1. And in the opposite direction, for every bicolored connected planar graph, we can obtain Belly functions, which is unique up to this change, such that this descent is isotopic to our graph. So it is nothing that Riemann existence theorem, so it's not something else. What is really interesting is that the absolute Goulart group acts naturally on the equivalence classes of descent. And the study of the section is actually what is called Grothendieck theory of descent on fun. So it is related to number theory. However, these descents are also closely related to analysis. And for example, the remarkable result of Bishop states that for any compact connected set and any epsilon, there exists a Belly function, even polynomial Belly function, beta, such that this descent approximates k to within epsilon the Hausdorff metric. And especially in view of this result of Bishop, the following problem seems to be interesting. So assume that we have a descent. So to again, descent is a graph, okay, but it is also something which is already exists inside of our sphere. So to what extent the set, this preimage itself, considered without graph structure, we call this support of descent, determines the descent. So in other words, under what conditions the equality holds for Belly functions beta 1 and beta 2. So we can see that actually it is a particular case of the general problem about preimages of compact sets. So it is particular from 2 points of view. So first we consider only very special rational functions with only 3 critical values. And then we also consider a very special compact set. But still, it is a particular case of this problem. So explicit example of descents like that are provided by segments and circles. Okay. Now, let me recall that Belly function corresponding to a segment is a Chebyshev polynomial. So just we use again. So just to remember you, so to recall you, if you don't remember that here is these two things, but instead of power, we will see something else. But still, we still have a very special compact set. So, so Belly function corresponding to a segment is Chebyshev, and Belly function corresponding to a circle is this function. Because z power n is not Belly function for this, that z power n is Belly function for a star. Okay, so the result is following. So if you have these Belly functions, let's assume also that they don't have a common right factor, then either both descent are segments or both circles, both descents are circles. And now I will try to explain the main steps in the proof. So let me start from recalling the following result, which was conjectured by Lang and proved by Hara 78. So it says that if the intersection of an irreducible curve with this thing is finite, so it's the definition groups of unity. So so it should be finite unless C is of a very specific form. So Carvalho, Master, and Zanien ask about a possible extension of the Lang statement where instead of the intersection with these things, we consider just intersection with the product of circles. Okay, so we don't care about the fact that they have finite order. Okay, we just consider all points with absolute value equal 1. And in particular, they prove that this system, particular system, where P is a polynomial, has finitely many solutions unless P is a monomial. So it's natural to ask what about the number of solutions of the system of equation like Z, where P1 and P2 are arbitrary rational functions, okay, not polynomial and Z, but arbitrary two rational functions. So, and we do have kind of solutions which are simply obtained from Blaschke products, and more precisely to say quotient of finite Blaschke products. It's just a function B rational which maps circle to circle. Equivalently, we can just write it in some specific way. And if it is a polynomial, then it's polynomial. This polynomial is necessarily monomial. Okay? It is give you a hint why previous result contained monomial. And so we with Igor Shparlinsky proved the following result. So if we have two complex rational functions of degree n1 and n2, then this number is bounded unless both these functions are some composition with some rational functions, common right factor again, so, and some Blaschke products. So of course, if they do satisfy this condition, then the level curves, this we'll speak about them, have a common component like that. So such bound cannot exist. But the problem is to understand that what happens if they have infinitely many points. And later, we with Stepan-Revkov proved a more precise version of the same result. So saying that the above bound can be reduced to this number. Of course, this number is always less than this number because it's, you can say that square is more than 0. So and this bound is optimal. So you cannot reduce it more. So now there's two approaches to proving this result. So first of all, let me recall that there is a classical object called lemniscate, which is defined like that. So, and the lemniscate coincides with a set of real points of numerator of this rational function. So the above question is equivalent to asking under what conditions such lemniscate have many intersection points. Okay, so here the approach is to consider this algebraic curve, really, use kind of Bezout theorem and so on. But the problem is, of course, Bezout theorem gives you something that like they should have a common component, but you should somehow prove that this common component is appears exactly if this condition is satisfied. This is the point. And another approach we used with Igor is just to observe that this map. So in other words, instead of Blaschke products, you can pass to functions with real coefficients. So it's the same thing, more or less, that consider functions which map real number to real numbers. And this is equivalent to say that R has real coefficients. Okay, and so, under this approach, you should show that some curve has many real points if it is parameterized by real functions. It's relatively easy because you can consider intersection of this curve with conjugated, and because you have the same thing, basically it should be defined at our real number and to continue. But now how to prove this theorem? So we have just 3 steps. First, we can use the above theorems. They are more precise because they give you some bound, but we don't need this bound. We just have to know that if this thing is infinite, then you can compose it with some W and some Blaschke product. And this is true because it's just part of your lemniscate. But now it's not lemniscate, but it's more real X, but still it is kind of, okay, because you consider part of this circle, so you can use it. So you obtain this representation because you can assume that they generate your field. You can think that you don't have here nothing called some real, some Möbius transform. The second step is to observe that if two rational functions generate the field, then the complete preimage of real x is only real x, maybe with addition some finitely many points, just because you can represent z as a rational functions of beta 1, beta 2, and so that give you some real points if beta of z and beta 2 of z are real. And eventually the last step, because you know this fact, you see that all multiplicities of your Belly functions should be at most 2. Because if you would have something like 3, you will obtain kind of star with 3h, and such star cannot sit in this real text. Okay, thank you. I finished.